I'd say is probably the trickiest part of this question. And if you're not sure where to go or you think you've got part of it, right, just move on, solve it, come back to actually deriving the differential equation. It's not worth spending a long time on, especially under exam conditions and time constraints. Okay, we're told a tank at a chemical plant has a capacity of 250 liters, not told what shape or anything, and it initially contains 100 liters of pure water. Salt water then enters the tank at a rate of 3 liters every minute. And this is important. Each liter of salt water entering the tank contains 1 gram of salt. It's assumed that the salt water mixes instantly with the contents of the tank upon entry. Let's just focus on that for a moment. So 3 liters enters every minute. That means 3 grams is entering every minute. 3 grams of salt enters every minute. So ds, where s is the amount of salt, ds by dt going in is therefore going to equal 3. Okay, we basically sorted out that term there. It's just the much more complicated term to now deal with. At the instant when the salt water begins to enter, a valve is opened at the bottom of the tank and the solution in the tank flows out at a rate of 2 liters per minute. Given that there are, yeah, then we're told that bit there. Okay, we need to think about this carefully. So, we've got it flowing out at a rate of 2 liters per minute. So I said when t equals 0, the concentration of salt is going to equal 0, because there's none at the start, over 100, because there's 100 liters at the start. Then when t equals 1, well, we actually don't know what it's going to be at that point, because we've got some coming in, but we've got some going out. It's going to be s over, now, it's going to be 100 plus 1, because we've got 3 liters coming in and 2 liters going out per minute. So 1 liter of water added each minute. And we can generalize this now. So when t is just equal to t, it's going to be S, the concentration of salt, over 100 plus T. And therefore, the S out over dt is going to equal -2 times that. Because that is the concentration of salt. There's 2 liters coming in. Sorry, there's 2 liters going out. So it's going to be that concentration multiplied by 2 that is then going out. And we just got to bring all this together. So hence, ds by dt will equal the amount going in plus the amount going out. We put a negative in there, so it'd be 3 minus 2s over 100 plus t. I think it's quite tricky, especially explaining like where it comes from. So I'm hoping I've done enough here. 3 coming in every minute. That's in the question. It's just all then about the concentration deriving this result. As long as you're justifying it sufficiently. The mark scheme is very brief, to be fair. They talk about the concentration, just go straight to this result. I've tried to kind of build my way up to it, and then we add them together. And now we've got to solve this equation, hence find the number of grams of salt in the tank after 10 minutes. So we need to find the general solution and then the particular solution. Remember at the very beginning, s is equal to 0. So I'm just going to write that here. T equals 0 gives s equals 0. Okay, this is a first order equation of a very particular form. We're going to be needing to use an integrating factor. So the form in general is dy by dx plus some function, doesn't have to be polynomial, sorry, times y is equal to some other function of x. And what you end up doing is you times by an integrating factor, which is e to the power of the integral of px with respect to x, both sides. And then you can basically absorb it and write it as a single derivative on the left. I'm not going to go into proving that here. I do it in other videos. So in our case, we need to get it in the right form. We're using s instead of y and t instead of x. And then here we go. I've got plus 2 over 100 plus t times s. That you can see the comparison. Here, my px is actually a function of t. It's right here. And then I've got my s instead of my y. And then that is equal to 3. So integrating factor is e to the power of the integral of 2 over 100 plus t. This becomes e to the 2 ln 100 plus t, which is then e to the ln 100 plus t squared. And now the e and the ln cancel, and we just get 100 plus t all squared. That's our integrating factor. So let's multiply through by it. We will get 100 plus t squared times ds by dt plus 2 lots of 100 plus t is equal to 3 times 100 plus t squared. Okay, and now I can write the left-hand side as d by dt of s times 100 plus t all squared. And you can check that. If you use the product rule, we would differentiate s and get the ds by dt and times by that function. And then we would have, oh, sorry, I missed an s out, I've just realized. Then we would have s times the derivative of this, which is 2 lots of 100 plus t. Perfect. Because now this is set up, ready for an integration. We integrate both sides with respect to t. And the left-hand side simply becomes s times 100 plus t all squared. Because I'm differentiating and integrating, it just goes back to the whatever the integrand is, the thing that we were differentiating. Right, I've got to differentiate this one. I'm going to get 100 plus t cubed. I'm going to divide by 3, so actually we just get that, plus an arbitrary constant. And that means that s is going to be 100 plus t plus c divided by 100 plus t squared. Arbitrary constant is absolutely vital here. Otherwise, it would just be this like linear function. So I always say to people when they're doing A-level maths, and they kind of get away with it, like you might lose a mark if you forget the integrating constant. Here, you can lose so many more. It's absolutely essential part of this function. So remember, when t is 0, s is 0, and therefore 0 is going to equal 100 plus c over 100 squared. Rearrange. C over 100 is going to be minus 100. C is going to be minus 100 times 100 squared. It's actually going to be minus a million. I think in the marks going to write minus 10 to the 6. I'm going to go with the 4 million. And therefore S is 100 plus T minus a million over 100 plus T squared. And just a reminder, we were actually asked to find the number of grams of salt after 10 minutes. Of course, we had to do this first. We had to find the particular solution. So when t is equal to 10, just sub it in. We're going to get 110 minus a million over 110 squared. And that ends up being 27.35 or 27.4 grams. When the concentration of salt reaches 0.9 grams per litre, the valve at the bottom of the tank must be closed. Find the nearest minute when the valve would need to be closed. Now be careful here. It's all about the concentration again. So we want S, remember, is the amount of salt, and the concentration after time t was 100. Well, the amount of the volume of water after time t was 100 plus t, because we're adding a liter every minute. So we're looking for when S over 100 plus t is equal to 0.9. Okay, just be careful though. Don't be setting S equal to 0.9. It's S over 100 plus t. And that means S is going to be 0.9 times 100 plus t. Right, we can sub that in to here now. So we want to solve 0.9 100 plus t equals 100 plus t minus 1,000,000 over 100 plus t squared. We get 90 plus 0.9t here, and we can rearrange. So it's 1,000,000 over 100 plus t squared is going to equal 0.1 t plus 10. Multiply through. So 1,000,000 will equal 0.1 t plus 10 multiplied by 100 plus t squared. Let's expand that out as we go. So 10,000 plus 200t plus t squared. And then that will give us, okay, be really careful here as you go, 1,000t plus 20t squared plus 0.1t cubed, then plus 100,000 plus 2,000t plus 10t squared. Okay, let's just tidy that up. We get 30t squared, 3,000t, and the 100,000. So we want to solve 0.1t cubed plus 30t squared plus 3,000t minus 900,000 equal to 0. We've got ourselves a cubic to solve. Okay, don't be trying to do this exactly or anything. Just use your calculator, of course. And, you could times through by 10 if you wanted. There's no need. Just type it in carefully. 0.1, 30, 3,000. And remember, minus 900,000. And we get 115.44. And then we get a couple of complex solutions. I say that we get complex solutions, but we're going to reject them, which means the nearest minute is going to take 115 minutes to reach that concentration. Wow. Finally, we're asked to evaluate the model. Now, I think I didn't get the mark here, so I just wanted to check that the tank wasn't full after 115 minutes, because remember, there's a capacity of 250, so I thought surely they're referring to that in some way. So I said, when t equals 115, the tank will contain 100 plus 115 equals 225 liters. So, yeah, not at capacity when valve closed. So model is valid. I feel like I'm evaluating the model, you know? It doesn't say what's wrong with the model, it says evaluate it. But actually it's looking for you to say what's wrong with the model. So this is not in the mark scheme. I felt like I'd be hard done by if I didn't get a mark for that, but of course I'm a bit biased. So actually what they were looking for are some problems with it. So you could say the model will only be valid when the tank is not full. Um, Yeah, I get that. When the valve is closed, the model is not valid. See, I'm saying it is valid when it before it's closed. But I think that's something I've learned from it. Just look for flaws in the model, basically, if it asks you to evaluate. It's unlikely the mixing is instantaneous. That's a good one because we're assuming it's like straight away mixed in. It's unlikely that the concentration of salt water entering the tank remains exactly the same. You could also go with that. All right, all I can do is tell you the mark scheme here. I think my answer is pretty good, but that is what they're looking for. Well done.